Rajashekar. I have to tell something before he comes here. He is my first batch student of digital system. In fact, he got job in TCS at the beginning. So once we get campus placement, yes, happiness, satisfied. We'll be in our electronics language, saturation reach. We don't need to do anything. But still, we both worked hard. That time we don't have Cadence, Synopsys, ANSYS. All these softwares are miles to go. We don't even listen to them, or we don't even, they are not at all our reach. That time, LASI, Lossy, is a software he downloaded. That time that is not even P2 system. It used to take almost 1 day to complete one small 4-bit CPU. But he developed a 4-bit CPU in 2002. Because of his experience in VLSI, he moved from TCS to Cadence. Then he will tell his journey. And instead of me, he will tell his journey. So that's what that. So now he is in core company. Otherwise, TCS also would have been in the top position, but he is now teaching us. So that is the difference, right? So I appreciate, and also he hardly, whenever I was contacting, he was not at all lifting. He was very busy. But at the last, maybe he committed, and he said that I will come on Friday, and he's going to spend time with us. So he's very enthusiastic, and we look forward, department is looking forward to take your expertise in several dimensions, not only this. In fact, thank you for coming here.
So let's try to get started. So I put a very simple agenda, just a 4-bullet agenda. I don't want to spend much of time probably giving all the experience I have gained. I don't want to give that big gyans to you. So I want to stick myself as a student. I want to be in your shoes. So you're all students. So I want to be presented as one of your peer, like one student presenting to the other student. So that's how I kept it very simple. Okay. So I was talking to sir also before the session, asking what should be the agenda, how do you prefer to keep it. So sir suggested that we will just put some landscape on India semiconductor. You know, there is a lot of, how do you say, like a lot of boom around India semiconductor in the last couple of years, right? So there is a lot of boom. So I'll just introduce what is that boom about, how that is going to shape us and you specifically as engineer. Okay, so that's about India semiconductor ecosystem. Then I'll also share, like basically as the title suggests, what are the hurdles in semiconductor IC design. Okay, so this need not be specific to India. This is like a global hurdles that a semiconductor IC design face. Okay, so what I'm trying to do is I'm trying to coin some terminologies to you. You are all well versed, you are all quite intelligent. So you guys can always do a Google and find out what it is. But as an objective, what I came here is to introduce you some of these hurdles so that you go understand what are those hurdles, how they can help you as an engineer, as a VLSI engineer. Okay. So by the way, how many of you are with VLSI digital systems or those specializations? I heard also that there are some folks joined here from Srinidhi. So who's from Srinidhi? Oh, good. That's good. Okay, good. So by the way, I am the first batch passed out from Srinidhi. Okay, so Srinidhi started in 1997. Yeah, so Srinidhi started in 1997. So 2001 was the first pass out, so I was part of the first pass out students. So I don't know, you know or not, there was a Professor Narasimha Reddy sir. So I don't know if he's still there. There's a college with his name also. Okay, so he was a very strict professor. It's a different story always. So he was the first, you can say, the principal in engineer who used to ask leave letters. So he used to be so strict. So if you are down with fever, he used to ask, give me a leave letter, get it signed with your parents. So it was that strict it was. Okay, so anyways. Okay, so I'll move that, and then, so some of the hurdles that we see, as you should know those hurdles, and then how is industry translating those hurdles into new horizons. Okay, so those are something which, again, new terminologies for you. I want you all to take some takeaway from here, saying, okay, these are the different terminologies I learned from it. Okay, so I'm happy to answer any questions you have, so I can take up those questions, and I'll conclude with whatever the government initiatives has taken, where are we, okay, how is it shaping up. I'll just conclude with that. Okay, so that's the agenda I have. Okay, so let's get started. Now, this is like a a very good chart. And then, I mean, this is the ecosystem in India, where since 1985, these are like kind of some organizations you have in your, in India. Basically, if you'd see, right, so yeah, so these are like basically the fab ecosystem and then the manufacturing supplier ecosystems, okay. So these are the two different organizations we had so far in India specifically. So this side on the left side is all about the design or the virtual fab ecosystem, okay. So Sanjeev was telling we have a fab system, but it was just a virtual fab system. So these are the organizations we have. Same way, we also had some manufacturing supplier ecosystems, like there were some equipments and tools available for us to do some manufacturing, strategic facilities, okay. So there were some facilities within India to it, and also there are some fab consumable, meaning like someone who is doing a fabrication. There are companies in India who provide their products or consumables needed for the fabrication, okay. So these are like a large scale of companies we have in India since, like, I can say around 30 years now. Okay, so that's how it is. So one key message you guys have to take is like India houses 20% of global semiconductor design engineers. Okay, what it means is today worldwide, based on the semiconductor design engineers we have, 20% of them are in India. Okay, so you guys should also understand that India is a hub for a lot of design engineers in contrast to the other countries. Okay. So that is one key good thing. Now, what do India semiconductor opportunity lies? Where does it lies? Okay. So if you see the kind of how the market share is going on, India in 2020 was approximately 15 billion. Okay. Now in 2025 we are around 64 billion, and by 2030 it is expected to be 110 billion. Okay, this is basically the kind of different software, AI, hardware, all these things come under the market, semiconductor market, and we are going to grow with CAGR, like it's a compound annual growth rate at 22%. So as you can see, so it's basically we are about to reach 110 billion. And as I said, it's basically, I mean, overall from this VLSI industry worldwide market, we will be around 10% of the market capitalization. Okay, so India would have that much thing. Okay, I think there are some things getting dropped. Okay, that's okay. So now what do we have is like we have some growing consumer business and marketplace. So that is where we see India as a growth opportunity. And also there are some different white goods, electronic goods, where India is kind of a strong manufacturer. Okay, so so that perspective, India has a lot of scope for growing in semiconductor industry. Okay, so this is just a just a way of understanding how the growth is expected. Now, now comes what government of India is doing, right? So I was talking about boom, which is coming, and there's a lot of I don't say noise, but it's a good noise. Okay, so as an engineers, it's always a good that there are a lot of initiatives happening in the government of India. So what happened is, if you look at, right, so there are basically three incentives or outlays that government of India has laid. Okay, anyone aware of what are these? Anyone seeing it earlier? Anyone knowing this upfront? So, so basically, government of India has come up with three plans. Okay, one is on the semiconductor and display ecosystem. This is what Sanjeev was also telling in the beginning about India in phase 1, they are going to do about semiconductor and display ecosystem. So that is number one. And then there are some other incentives also planned, like incentive number 2 and 3. So these are mostly for electronic manufacturing and considering different sectors for basically large PLIs. Okay, PLIs is product linked initiatives. Okay, so so there are a lot of terminologies here. I would suggest, like, whenever you get these handout or the slides, right, so you can always Google them. These are very little acronym intensive slide, but you can easily find them everywhere in the Google. Okay, so so if you look at now, right, so today the India semiconductor is focusing on this first one, where they are looking at creating this semiconductor fabs and display units. which is under this Indian Semiconductor Manufacturing BU. That's a separate BU formed under Ministry of Electronics and IT. So that is taking care of this semiconductor fabs and display thing. Similarly, compound semiconductor, which I think Srinivas covered, right? So, and then the most important thing is assembling, testing, marking and packing, ATMP. So this is the other thing which is kind of a focus. Then there is something called design linked incentives. Okay, so there are like, as you know, there are two components. One is designing part, another is the production fabrication thing. So on the design side also, Government of India is giving some design linked initiatives, incentives basically. Okay, so what are those, we'll get to know. Okay, and then modernization of semiconductor SCL lab. So as like we know, there is this SCL lab in Chandigarh. So there are also plans to modernize it, because that's the only fab we have in India, like as we came to know in the previous session, right? So that is also part of the first incentive outlay. Okay. Apart from this, there are like production linked incentives like for mobile phones, components and IT hardware. Then there are other incentives which Government of India is creating. And then the most important is development of these electronic manufacturing clusters. Okay. So these are like kind of different clusters which Government of India is going to come up, where in different regions they are going to focus on developing VLSI companies or VLSI ecosystem, right? It can be design, it can be fabrication or anything. So they are calling it as these electronic manufacturing clusters, okay, called EMC. Okay. So this is part of the second initiative, and then the last one is more focused on very specific or high demanding areas. For example, this advanced cell chemistry, automobile and auto components, right? So these are the very, I think, telecom and networking, solar and PV modules. Like we know everywhere it is now solar, right? So it's just completely booming there. And then white goods. White goods are basically the kind of the daily electronics that you use, refrigerators, coolants and everything. So those come under white goods category, okay? And then IT, hardware and other electronics. So there is a big incentive planned for taking care of these sectors, where Government of India is going to release these respective amount of money to develop those sectors. Okay, so that is why unless there is some money coming from somewhere like Government of India or private and public partner players, so you cannot see a growth in any industry. Okay, so that's where Government of India has started initiative where they kind of focus on all these different outlays to focus on electronic semiconductor. Okay, so hope it's clear like what are the different areas that they are planning to do. Okay, as part of the first initiative, some of it actually in the previous session is done. So I mean I can say we both are from Synopsys. Some of our slides are also common, okay, so it's almost the same pulse that we are talking, okay. So here, so what we have seen is like they have already started their first semiconductor fabrication unit in Dholera, Gujarat. So this has already been done, has already been started, and there are some 4 cutting edge chip assembly and testing plants, okay. So you'll use very frequently this chip assembly and testing plants. Okay, so this is basically for assembly, testing and packaging. Okay, so these are the different things you have to do as part of the things, and 3 units in Sanand, Gujarat are already started in the sense like they are getting ready, and then 1 in Assam is also getting ready. Okay, so these are kind of the kind of support which we are getting from the Government of India, and these are like very expansive plans being done in India level. Okay. Okay. So now, how many of you are aware of this word called semiconductor value chain? Especially from VLSI, who's doing VLSI digital systems should have some understanding. Any idea? No? Okay. So semiconductor value chain, what is it about? Okay, so if you look at the semiconductor or IC VLSI industry, so unfortunately there are small fonts you cannot see, but I'll try to pinpoint each one to understand to make you better. Okay, so basically if you see, right, so basically the semiconductor involves 3 things. One is design, fabrication, assembly and testing. Okay, so you can say this is the supply chain that in a VLSI, you would have three key stages, like design, fabrication, and assembly. Okay, so here if you see on the top, right, on the top left thing, these are fabless designs. What I mean by fabless, they are the companies, they don't have any fabrication. Okay, so they just rely on designing the chips. Okay, their focus is just designing the chips. Okay, now these design, fabless design, go to whom? The middle one in the top, these are foundries. Okay, so who are foundries? Manufacturers, exactly. So they are the ones who manufacture your design from a design company, and you can see there are the big players here like UMC, Global Foundry, TSMC. These are the big players in the foundry. Okay, now for them, actually once that foundry part is done, now what foundry would do is they would go to something called assembly, testing, and packaging. Okay, ATP, that is what we call ATP. So once the fabrication is done, it goes to testing, packaging and testing. So like if you see here, so once fabricated, the silicon wafers contains many small dies that must be cut, tested, and packaged. That's what these folks will do. Okay, so design, fabrication, and this is packaging. Okay, okay. So these are the kind of three key things. Now, for them to work, okay, for these three kind of stages to work, what are the inputs for them? Okay, one is ARM, and they are called as design IPs, right? So where these design companies get some IPs, right? You get some PCI IP, you get some USB IP, UMC DDR IP, right? These are different IPs that are sent, ARM IPs. You know, a lot of people know ARM, right? So ARM IPs, so these go as to the design inputs. Then you have something called EDA, Electronic Design Automation, where I am part of it and I am working in the Synopsys, right? So we give the tool to the companies and they kind of make the designing happen. Okay. Now, same way for the foundries, what you do is you have to give the equipment, right? Foundry cannot just make the chip or anything. They come up with the spec on how the node should be, but the fabrication equipment and all will be given by these organizations. Okay. Same way you have raw material, right? The silicon or whatever you do, the mask which are there. So all that needs raw material. So these are the organizations that provide the raw materials. Okay. So one is this, the other one is equipment providers, and the last one is something bigger players called integrated device managers, device manufacturers, sorry. Basically they are IDMs, called in VLSI industry they are called IDMs. So these are the big players who has all design, fabrication and packaging together. Okay, so that's why you see some big layers like Samsung, Intel, Micron. So these guys have their own design, manufacturing and also testing things. Okay, so they are called IDM. So all these different players are kind of part of the semiconductor value chain. Okay, so I mean I'll pause here. Any questions? Anything before I move on? Anything value chain? Anything didn't understand? Okay. Now, so that's the basically what are the different things associated with it and what are the kind of how the ecosystem, overview of ecosystem that I shared. Okay. So now we'll shift some gears and looking at what the government is doing and all. Now let's look at what you as an engineer, what everyone as an engineer, as working engineer and as an academic engineers, what are the things that you would be coming to know. Okay. So first we'll start with hurdles. Basically let's understand the problem. Okay. So when you go to a doctor, first you tell your problem, then he'll give you a medicine. Okay. Same way, let's understand what are the problems first in the VLSI design industries. Then we'll try to understand how VLSI industry is growing to change them into different horizons. Okay. So that's what I'll cover it. Okay. Now, so what are the different basically initiatives that has been happened, right? So I was telling you in the previous 1-2 slides back. So this is where the focus is all about, right? And I am saying that now the focus is more on this ATMP thing. As a first initiative, they are taking up these initiatives, these things, and main focus is on this assembly, testing, marking and packaging. Okay. There's a reason why government choose this, okay. So in the next slide which I cover, you'll get to know why India chose to be a leader in testing, packaging and marking things, okay. So assembly, testing and manufacturing, what is the reason for it, okay. There's a very logical and very reasonable say for it, okay. So if you see, right, so generally the fabrication facility, I mean, how many of you know what are the fabrications, where are the fabrication units, which countries have fabrication? Taiwan, right? So where TSMC is there, correct? That's a big player, correct? So now for us to come up, right? So those fabrications are always highly capital intensive. That means for someone to start a fab, right? Say even for in India or any other country, right? Growing economic country, setting up a fab is a very capital expensive, right? It needs the billions of dollars, right? That is one thing. Now, whereas when you come to assembly part, right? So assembly is more labor intensive, okay, where it is built with a lower cost and it's always attractive, okay. So no, I mean, to bring up an assembly, you don't need a large money or anything that needed. So you need, all you need is the labor to make it the assembling and testing and packaging, okay. So that's another thing. So that's why we kind of started off with this assembly ATP. Basically that's, I'll frequently use ATP, assembly, testing, packaging, okay. So ATP. Now, what is ATP? That is basically the companies who can do them together, okay. Not every, I mean, not one company can do all the OTP thing, right. So something what we have, something called OSAT, okay. Basically it is outsourcing semiconductor assembly and testing, okay. So someone would do your fabrication and all, and you outsource to someone else to do your assembling and testing, okay. So there are companies who do only OSAT, okay. They don't do design, they don't do anything, they just do OSAT, basically so outsourcing semiconductor assembly and testing, okay. Now if you see the market share, overall OSAT market share, it is like 81% of it is in Asia. And if you see, right, so from this 81%, 38 and 37 are taken by China and Taiwan, okay. Any reason why again Taiwan and China? Why it has gone to Taiwan and China? The clue is in my previous bullet. It is labor intensive. They are cheap, I mean you can say like they are low cost labor or employees available there, right. So that's why if you see OSAT, most of the assembly testing is all there, because they are compared to US, which are in dollars. These folks are, I mean, much more available than those in the US or another UK or those regions, right. So that's the other thing. And if you look at the overall OSAT facilities, right, so there are around 370 OSAT companies, okay, organizations worldwide, out of which 42% are in again China and Taiwan. Okay, so that's also signifying that China and Taiwan are kind of things, and only 12% of them are in US. Okay, though US is more known for design thing, assembly and testing and packaging is not available there. Mainly because lack of labor or skilled employees there, it's where US is not having OSAT. Okay, same way OSAT market growth. Now one would understand, okay, there is something at OSAT, but is there any money which I will get from OSAT? Right, so this growth will tell you how it is. If you see, right, so in 2024 it is around 43 billion market. Now in 2029 expected to go to 71 billion. Okay, this is just $1 billion we are talking. Okay, now clearly these are one of the sectors within the semiconductor where everyone is focusing about. Okay, so that's why India chose to do on AST, okay, AT, basically testing and packaging, ATP, so that they can focus on this market where your incentive is less, where you have to put less money, you have a good amount of skilled engineers or labor, in other words you call, so that way they have taken, okay. Correct. So yeah, I think in overall actually even in the skill also there is not much large gap between those two regions, okay. So yeah, I think maybe, yeah, sure, no problem. It's a good question, but still, I think it's clarifying what is what and how it is. No problem, yeah. Okay. So that's what it is. So I think this is where I'm trying to bring up why India chose ATP specifically, because there are a lot of factors associated with it and there are some advantages with ATP, right? Yes. Yes, yes. Okay. So that's how it is. Now we'll try to understand what are the different hurdles are there in a design semiconductor industry. Okay, so this is where I want everyone to understand different terminologies when someone is designing, like when I did my 4-bit ALU kind of thing, right, full adder and all, right. So what are the things I had to consider, right? So there are different terminals. I was focusing only on designing part, where I know I have to put an RTL code, do some simulation, and if the results are matching, I'm done. So that is a very small domain which I used to work. But after coming out in the industry, there are lot many other things what associated with semiconductor industry. Okay, so all that I want to bring up here, so that there are some challenges. Let's start with challenges. What are the different challenges associated with the semiconductor industry? Then we'll go how industry is shaping itself to overcome those challenges. Okay, so that's where it is. I think the first and foremost thing overall is that we are actually complexity of the design. Okay, so this is the first and foremost thing. Year after year, the complexity of design is growing significantly. Okay, so it is going from 1x, 2x. Moore's law said 2x, right? So every 2 years, chip density will double, right? So if you see, there are large number of billions of transistors are getting integrated into a single chip, right? So that's where I'm saying increasing the transistor count. That's what I say complexity of design is significantly increasing, right? Now, with that increase in the transistor count, what is the challenge we face? We face that you have to do that circuit designing part, you have to do it the testing part, and also the verification. When I say verification, I mean the functional verification, right? So that's, I mean, designing is one beast and verification is the another bigger beast, right? So that's altogether a different thing, correct? So that is one thing. And then with the complexity of design, your power management also becomes even more challenging, right? So you have a lot of power consumption, you have a lot of heat dissipation challenges, like something which I think Sanjeev nicely clearly covered, right? So that's what it says, right? Power management. Same way, I think another challenge is process variability. Okay, so when I say process variability, our job is just designing, making sure an AND is there. You connect the set of AND things and do simulation, right? But in reality, it is not exactly the same AND goes it. It has to be manufactured, right? So there are some manufacturing variabilities associated when you design something. Okay, we are talking as an engineers at academic level, we talk at ALU, 4-bit ALU, which has maximum say 500 or 1000 cells. But in design industry, it's all millions of cells, right? How will you manufacture all of those without having any problem, right? So that is where it is called as manufacturing variabilities. Okay, so basically there will be a lot of inconsistent transistor behavior which can make your chip to fail. If there is no proper manufacturing done, right, so you will have a high chance that you will kind of fail the chip functionality just because of manufacturing. Okay, so that is one thing. And obviously when there is a variability, it automatically impacts your performance, power and reliability. Reliability meaning the long duration of a chip, right? If you prepare a chip, how long it works, that also gets affected. Okay, and another challenge with process variability is the scaling limitation. That means when I move from lower nodes, right, like 5 nanometer, 3 nanometer, even now there is a 2 nanometer technology node, right? TSMC is coming with 2 nanometer as well, right? So on those things there is, I mean, when you make a lithography things and all, right, there is a high chance that you will change the kind of functionality, and then how can you grow, I mean, as you shrink smaller and smaller, right, manufacturing becomes even more difficult. That means there is a high chance that your cell might become a failure, correct? So that's where it says there leads to a lot of design unpredictability. You prepare a design, you send it to fabrication, but it doesn't function the same way, right? So that's where there are a lot of design unpredictability, right? So that is one challenge we have. And the other thing is design for manufacturability, DFM. Okay, this is also a very niche topic. IITs and all, they just have DFM as one of the specialization. Okay, so that's how intense it is. So here what we talk about is about yield optimization. So when I say yield, what I mean is, let's say I come up, my foundry makes say 1,000 small chips, right? How many of them are working? Say out of 1,000, only say 800 are working. So my yield is 80%, right? Say from the 1,000 in the lower nodes and all, if only 100 are working, then my yield is just 10%, right? So if that means you are saying that when I give my design to a foundry, only 10% of it will work as a proper chip. Rest 90% are all not in use, right? So that's how complex it is. So lower nodes, there are very less yield nowadays, right? So that's one challenge we have to do to make it. And then other thing is the mask cost, okay? So the mask is basically how you create different layers in your fabrication. I mean, in VLSI you see, right, there are different masks associated. A lot of people, when you transistor, how a transistor is built, you might have heard about the mask cost, right, different masks. So the cost of each mask is very expensive. Like in the beginning I said, in my previous slide, I said, right, so the fabrication is very capital intensive, right? So the fabrication and everything associated with is very expensive, okay? So that's one thing. And also you cannot afford to do multiple production of the same chip, okay? So even if there is a certain mistakes in your design, each mask fabrication cost is in billions of dollars, okay? So as a designer, you have to make sure everything associated with DFM is taken care, so that you manufacture only once, okay? If for once it generally costs like 350, 400 billion dollars, if even a small mistake is there, that company loses that much of money, okay? So that's how the DFM is a challenge, okay? Next is the verification validation, right? So this is also one of the bigger challenges, because your complexity is increasing. Obviously your functional verification and everything, number of scenarios to test, number of edges to validate, all those things are significantly high, okay? So that's where we have to use your simulation tools, formal verification, emulations very extensively. Only then you can ensure that all your functionality of the chip is in a safer hand, or you can guarantee that functionality, right? This is on the front end side, functional verification. Same way we have timing closure on the back end side, where with increased complexity, right? So there are functions, different functions available today. So sign off becomes even more tricky, because you have to add more and more sign off scenarios or corners, okay, PVT corners which we call, right? So those things are there. And of course the process variation factors are kind of becoming more and more predominant, right? So that's on the challenges on the verification and validation. Same way you have on advanced node challenges, right? So I was telling you, we are shrinking lower and lower to smaller nodes, right? So after 2 nanometer, anyone can tell what is the next node? No, FinFET is already there. No, I'm saying the node, let's say 5 nanometer, 3 nanometer, 2 nanometer, what is the next number? So Armstrongs, exactly. So Armstrong is where it is moving towards, right? So that's where we are moving towards. And 18 Armstrong is the one which currently in discussion. So let's see how it comes. But now again, in the advanced node also, there are a lot of quantum efforts like tunneling and all these things, where it leads to a lot of leakage and power. So that's other thing. And as someone said, FinFET and all, so we have to do a lot of innovation in transistor architectures, FinFETs, GAAs, gallium arsenide, this thing, right? Gate all around FETs, right? So that's the other thing. These are the different kind of transistor technologies we need, not just CMOS, right? So those things. And also with advanced node, obviously the interconnect delay, right? So you have two back-to-back inverters, right? How are they connected? You connect through a net or a wire, right? So that net is nothing but your net, and the cell gate is basically the gate. So your delay in a circuit will be the net interconnect delay and gate delays, okay? So with advanced nodes, what is happening is your interconnect delays are more than the gate delays, okay? So you have to be very careful when designing the number of buffers you are using, you cannot just blindly use as many buffers as you can. Clock tree synthesis, I know if someone in PD, they know what is clock tree synthesis, right? So routing and signal integrity, these things you have to kind of take care upfront. I mean, these are basically different challenges you are getting in advanced node. Okay. So same way the parasitic modeling, when I say modeling, with shrinking node, the foundry gives what is the characteristics of each layer, what is the R value, what is the C value, correct? So those characterization are becoming more and more stringent, and as an engineer, right, so you need a lot of extraction simulation models to say that, okay, if I use this metal layer, this will be my RC value, okay. So that's how it is. And same way EM, I think electromigration is how much of a current layer can withstand, right? Electromigration anyone knows, right? So basically there you also need to have a proper planning of your current density, right? You don't want your layers to have lot of kind of current taking through, correct? So these are basically different challenges you have across. There are a couple of more things like thermal power dissipation. Again, with lot of complexities and ICs, it becomes more challenging that how do you take care of the heat generated by the chip, right? So today, if you take any laptop, right, if you put it on a lab, suddenly after half an hour it starts getting heated up, correct? So it's just an example. Now same thing happens to your mobile. If you are putting it into a high performance, it also heats up, correct? So how are the industry taking care to get away those heat generated by those complex processors, right? So that becomes also one of the challenge, correct? And again, how you consider the power gating and leakage, right? So in previous session we saw your transistor can be turned off, right? When it is in ideal mode, what you should do to how much power it consumes, right? Say for example, a simple example is your mobile, right? In the overnight, if you are not using it, it's in the ideal mode, correct? So in that case, ideally expectation is it should not consume any battery, but sometimes it takes up 5%, 10% thing, right? So still there is some leakage current passing through, correct? So you have to take care of that. And at the same time, when you bring up your system, any system, suddenly because of the power gating designs that you design, there is a very high chance that you push lot of current at a time in the design and it can cause to failure. So that's one challenge today the IC industry is facing. Okay, so and then second one is, basically the next one is on the design time and cost constraints. Okay, so what I mean by design time, okay, so is it that like for a project, anyone to do a project, you get a thesis work for 6 months, right? So that is you get a predefined 6 months to work on that project or any of your ALU or any design, right? For the design, that's not the case. Design has to come to a market within 1 month, 2 months, or maximum 3 months. Otherwise, some competition will come and take away that functionality and he will use it, correct? So simple example is Qualcomm and MediaTek. These are the two companies that gives processors for your mobiles, right? With one specification, say Qualcomm comes up with a spec, and if they take 6 months, MediaTek same specification, they come up in 4 months. So where will the manufacturers like Oppo or Vivo or Nokia or Samsung, they would obviously go to MediaTek because they are giving you faster, right? They will be ready to release even Oppo or anyone want to release it faster, correct? So that's where it becomes more time to market pressure is significant nowadays, right? Because there are lot many players, lot many competition, lot many challenges. So this comes to a forefront, okay? Same way tool complexity. So if you look at the tool complexity, there are a lot of challenges with complexities with the kind of things. One is like EDA tools. Lot of tools, not just basically the very basic model, they are also coming up with AI variant, lot of tools that supports AI based modeling, right? So that's one thing. And then licensing cost is also another factor. Like for you, when you use Synopsys or Cadence tools, automatically there will be certain license cost, right? For academic, it is little smaller, but whereas for the industry, they charge as per the market rate. Correct. So those licensing costs are also very increasing as you increase your design complexity. Same way, as a designer, if there are complex tools, obviously you should use those tools, right? As a designer, you and I should use the tools. So it becomes also a problem or like a challenge for us to learn those tools, get used to those tools, and then put it in the implementation, correct? So these are different challenges. And of course, security and reliability. Nowadays, security is a big concern where a lot of things are actually being hijacked or, are vulnerable, correct? So those things also you should take care when you are designing, right? So these are different challenges we have today in VLSI industry. So I brought up a lot of topics, a lot of things. But these are something you go back, think about it. Okay, in the VLSI industry, it's not just designing, connecting my 4 AND gates and NOR gates, bringing a full adder. If I give a simulation, all inputs, zeros, ones, and then if I get output, that is done. So it's not just that, right? So there's a lot of things associated. So all the challenges that I mentioned earlier are all that something you should look around. Okay. As an engineer, I want everyone to go and check up all those individual topics, understand what is the background, how critical it is, because they are all part of the semiconductor value chain, correct? These are all interlinked, designing, fabrication, packaging, everything is interlinked, correct? So what you are working is more on the design side, just a small part of the design side. But the entire ecosystem, you should be aware so that when you discuss or go out, you get to know all these things, okay? So when I was doing same thing, the Lassie tool which sir was telling, so I was also focusing on that because at that time I was also not aware of it. But only through experience I came to know these are the different things you would. Right now you are getting a readout of what are the different challenges. So you should be kind of thanking or should be very happy that you are getting to know all those challenges. So that's the kind of message you should take. Now I taught a lot of hurdles so far, right? So I said I have so much disease and all. Now the task of giving the medicine is there, correct? So here I'll put only 2 slides, okay? So that means my hurdles were all 4 slides. There are many challenges, but the designing part we are taking care through some better means, okay? So what are we taking care to address all the things, okay? So scaling beyond Moore's law, correct? So everyone knows Moore's law, right? Right, correct? So that's good. Even non-VLSI should know what is Moore's law, by the way, okay? So that's in the Moore's law, what is it, right? So basically we are slowing down because our silicon-based manufacturing is getting a limit, right? In the previous slide, gallium arsenide, all those things are coming because silicon-based manufacturing is reaching its limits, correct? So now what we should do is there a way where we can scale more? Can we keep Moore's law alive, right? So we can say yes, but how is it? So that's how the industry, so that's what we are doing is, instead of doing a single die, what we are doing is something called 3D ICs. Okay, so 3D IC is, 2D is basically a plain kind of a thing where all the functionality you put it in a 2D and then they connect horizontally. Whereas 3D ICs is where you're stacking all your dies, right? So that way you are increasing the complexity. So it's basically high-rise apartments, okay? So that's how it is, the 3D IC thing. And also the heterogeneous integration. Basically what I mean by heterogeneous integration is multiple different functionality chips or dies can be integrated together, okay? So that's what 3D IC, that's what industry is moving towards to keep Moore's law alive, something called 3D IC and heterogeneous integration, okay? And again, looking beyond just CMOS technology, we don't want to stick to CMOS technology, we have to go beyond that. So that's where the carbon nanotubes, graphene, and all these are different ways to expand outside just the transistor. Another thing which industry is taking it is the newer styles of designs, okay? So designing is, I said there is a designing one aspect, but can we do it in a different way so that we can put more in a lesser area, correct? So that's where it's called something nowadays, some companies like AMD, those people are coming up with something called heterogeneous computing, right? So where you combine all your specialized processors like GPUs, CPUs, all those things, all the FPGAs, ASICs and all style of designs into single SoC. Okay, earlier there used to be a graphics card separate, a CPU card separate. These were all different in the processor thing. Now it is all single called APU, accelerated processing unit, which is combination of GPU, CPU together, right? So that's what we are calling it as like heterogeneous computing, all multiple functionalities, multiple processors together, correct? So that way it helps to you to design different tasks using your this style of design, okay? Then something called chiplet based designs, okay? 3D stacking is different, chiplet based design is different, where you are replacing your monolithic ICs with chiplets, okay? So where you are saying that your smaller dies are integrated in a single substrate, correct? So that way it gives you, instead of, let's say for example, simple different functionalities, you can keep it in a different things and then interact with them each other. So different chiplets kind of a thing. It helps you with flexibility in design and fabrication. Obviously, smaller dies you can manufacture separately and then integrate, correct? So it's also cost efficient from better yield standpoint, and also you help to get designs designed independently. You don't have to rely. Like monolithic single is entire design has to be done at a time. Chiplets can work in a hierarchical fashion, where designers can work parallelly on different chiplets, correct? That's one thing. And then generative designs. Generative is like the AI based designs, where some engineers are using AI to come up with their circuit definitions, and new architectures are also automatically coming with that, okay? So AI is coming with the newer architectures where you can design more complex circuitries, okay? Then how do I meet my power and performance things? Okay, so I told a lot of power gets dissipated, but how are we taking care? So we are moving to, always there has been a lot of focus on how can we design low power designs, basically chips with low power, right? So dynamic voltage scaling, now there is a concept called self-gating on the clock, right? Earlier you used to give enable signal to turn off a clock. Now there is something called self-gating for the clock, where clock automatically sees that it's not getting the signals, it automatically turns off itself, right? Turns on and off itself, right? These are different low power techniques available. Same way AI workloads, right? So you have a lot of power efficient AI accelerator, which kind of helps to meet, kind of balance the trade-off between power and performance on using the machine learning tasks. Okay, so these are different kind of power optimization techniques being used or getting introduced. Okay, next is advanced node manufacturing. Correct. Now I was telling we are moving from one node, lower nodes. Every 3 years, 2 years, we get to newer node. Correct. So that actually, of late, we've been introduced something called extreme ultraviolet lithography. So this basically helps you with a proper manufacturing of the layers, so that it gives a more precise manufacturing or layout of your design. Okay. So this is very extremely costly, expensive fabrication thing, which is available in I think starting from 5 nanometer, it started available. Okay. So any upper layer it's not available, but 5 and 3, 2 nanometers, these are available. Next most important thing is sustainability in the IC design. Okay. So you see a lot of nowadays, like a lot of efficiency, how can I sustain my IC design? Okay, you are designing your thing, like, you know, a long timer, if you are using a mobile phone, at max it stands for 1 year, 2 years, and then it starts having a lot of problems. Correct. Not just memory specific issues, but functionality point of view and all. Correct. So those things, it becomes more and more important that you focus on, basically design teams are focusing on reducing the power consumption at design level and across, and also about on this entire semiconductor manufacturing process. Okay, so these are different domains that they are working to improve your energy efficient designs. Okay, sorry. And another thing which is also nowadays, like how much you can reuse or recycle it, right? So we have heard recycling only in the ones which you dump, like plastic, paper, those things, right? Even there is a lot of study going on where the semiconductor waste is also very much causing harm to our environment system, right? So that's where we can see how much we can work on creating recyclable and also biodegradable materials, right? So there is a lot of research going on where these materials can be reused or recycled. Okay, so those are different domains which are working. And I think again, this is more very late kind of innovation kind of a thing, which says about quantum computing things, where I mean, quantum is basically, we have, so far we have binary kind of system, either 0 or 1, right? So quantum is like a spectrum of values which you have to design, correct? So that's quantum computing, and then you have qubits. There is terminology called qubits, which actually basically tries to interact with a lot of these classic electronics, right? It goes and connects with your classic electronics so that your functionality, all the electronics are working fine. Same way, for qubits to work, you need some cryogenic control ICs. Basically, these are also some of the ICs that control the qubits, and they work on, basically try to work on a different temperature altogether, right? So all those things are also being designed in our latest advance. Okay, so that's what I was telling in the beginning, that all those hurdles what we are seeing, basically we are trying to cope up or do better with a better style of designing, better style of manufacturing, all the reusability, all these things we are trying to translate those hurdles into our horizons. Okay, so that's what I have on the design part. Okay, I think, yeah, basically, so I think I just missed it, but again, all the hurdles in semiconductor are kind of taken care by a lot of enabled innovation, where we are trying to work on materials, tools, design styles, everything, manufacturing, all these things, all the ecosystem is going through an innovation, right? Only then you can take care all the hurdles that we learned in the previous slides. Otherwise, your Moore's law is already dead, correct? So we cannot consider that thing, right? So that's how it is. Okay. With that, I come to the last section and last one slide before your lunch. So, okay, so how do we looking ahead? So I'll just conclude with, I prepared some different conclusion, but today there was one government announcement from one of the Ministry of IT on what things have been done so far. So this is my latest, today's conclusion is based on latest press note. You can go and search exact, these numbers are there. Okay, so so this actually I felt is more relevant, where they are saying what so far in the last, I think 4 years, 2019 where this semiconductor initiative was started, in last 4 to 5 years what government has done or what government has achieved is all captured here. Okay, so this should give you an understanding that how the VLSI transformation is happening, and where you are, all your guys are in very good kind of state of mind, or like in a good era of innovation, or like semiconductor industry grow in India. Okay, so if you look at it, right, so basically the first bullet is kind of negative news, where it say the industry said that they are actually kind of almost like they are procuring or importing chips and ICs, memory chips of worth 1.7 lakhs crore. Okay, so India is spending almost 1.71 lakh crores in importing the chips from other countries. Okay, so that means this much huge amount of money we are giving it to the outside the country to get some of the chips, some of the components or ICs in the design, correct? So this much of money is going now, right? So now that's where, if we continue to do it, the way the growth the semiconductor is seeing, this number easily can become some 1.71 lakhs to 10 lakhs crores or any number, abnormal number, correct? Unless we go and make our own homegrown chip manufacturing system, we cannot continue to import those chips. Okay, so that's the message the IT industry or our government of India was telling today, saying that so much of imports we are doing, it's a high time that we should make homegrown chip manufacturing, right? Assembly, testing, packaging, all these things we are needed to sustain. Okay, so and then they have also announced that there are some 5 semiconductor chip manufacturing and assembly projects are approved. I said in my one of the slides, 3 I have mentioned in Gujarat, 1 in Assam. So today announcement said it is 5. I am yet to know what are those things. And also I think in the first initiatives, right? So one of the thing was DLI, which is design linked incentives, correct? So on that, under that scheme, they have already given like nearly 15 semiconductor design companies have been approved. Okay, so they have identified 15 semiconductor groups where they are going to get these design linked incentives for them to make their own chips. Okay, so unless they get incentives on the R&D to come up their own chips, they cannot manufacture or create a design, right? So government has announced that almost 15 such companies have been approved. Same way, there are actually 41 semiconductor design companies have the EDA tools available. Like in one of my slides I was telling, right, the licensing cost of an EDA tools is very high, right? So unless the design companies, which is a startup company, until they are getting acquainted with these licenses, they cannot design, right? So that's the thing. You give something, then you get some output, right? So that's where government has given up to 41 semiconductors with the proper EDA tools for them, correct? So that initiative has been done by the government side. Same way, we are talking, okay, we are growing industry and everything, right? So we are setting up the ecosystem, we are setting up the fabs industries and everything. But where is the man force? Where is the talent readiness, right? Even government should think about it as well, right? So that's where it has been announced that almost 25K students have been trained across 113 organizations under Chips to Startup scheme, right? So government is not just looking at expanding or creating the infrastructure, even the talent has to be grown, right? So that's where they are giving the training under this Chips to Startup scheme, where they are training all the graduates and undergraduates to come up and help in this India semiconductor industry. So and then again, and then they announced also saying that over a period of time, maybe in a couple of years, they plan to kind of train 85,000 manpower to have it in the chip designing, VLSI and this thing, right? So these are different initiatives that has been taken so far, okay? So that's where it says, and this is one last bullet I would finish or conclude where they say millions chips but billion dreams, okay? So that's what the government says. Okay, so though I might sound like I am a promoter of government, but this is how the India semiconductor industry is shaping, okay. So don't take me around that, okay. So this is the last slide I had, and with that I'll pause here. Okay, any questions, anything? It is 2 questions. One thing which you have learnt, design LinkedIn, thank you, very good.
Sir,
Sorry?
I have a question, sir.
Yeah, go ahead.
Sir, are only Synopsys and Cadence are the 2 tools that are providing for all the companies?
Not really. So those are the big players. There are Siemens, and there are other VLSI, I mean EDA tools that provide the tools. Okay, but yeah, okay. There is Siemens also provides EDA tools, some EDA tools things. So yeah.
I have a question. I think they know me. So actually, this is Dr. Ram. Actually, I have a startup in AI Tech Park in Penang, Malaysia.
Okay.
By the way, I work for Intel Malaysia Assembly Test Facility for 12 years as a senior test R&D engineer and operation research engineer, finally data scientist.
Okay.
Now I'm fully focusing on my startup company. And is there any opportunity, because our chip demand is right as a globally, why we need to crazy to go for new nodes? Can't we take up some fab from Taiwan or something where they are not using, like second-hand car we buy, right, to use to start with? So we can move the fab here, and that is a more, still we can support, right? So many chips doesn't require the top challenging nodes, why we need to worry and let them give the big task to the other people.
That's the, no, I understood
If you
your
see
question. Yeah.
the demand for 5G,
Correct.
6G chips, not much right now. As we have our need for this all so many chips where we can use the older technology, we can bring that one, like anyhow they are not using. So is there any initiative that thing is there? I would like to take part. Thank
No,
you.
no, actually, see, I think this is, I mean, in a layman terms, I would say this is man-made created problem, where we want all sophistication and everything. We want, yeah, we want more advancement, everything we want. We were not happy with 2G scams and all. We want 3G, 5G, 4G, everything we want, right? So it's like more innovation. Now we also don't want to work now. We want AI tools to do some work for us. We want robotics to do something for us, right? So yeah, yeah. So that's like a part of answers. I mean, saying that why there is so much of interest in advanced nodes and all, right? So to cater so much of sophistication of in the tools or design we want, that's where advanced nodes are more needed. Yeah, exactly, correct. So even our fabrication assembly and all, we are not targeting on the advanced node and all. We are still focusing on 28 nanometer, those bigger nodes only is the focus, right? Because that's the area where not many, I mean, there is a lot of production or things going, but that's where we are focusing it, right? So that's one part of the answer, and yeah. And then again, we want Moore's law to be alive, right? So we want more and more complexity and all, so we are making bigger and bigger chips. And to your other question on why cars, why can't we reuse and things, chips designing doesn't have much of reliability, right? So their life is maximum 2 years, 3 years in a best case. Whereas cars, you run for years and years and things, right? So that's where we cannot completely reuse the IC the way we reuse the cars.
Yeah, I'm Abhigna from Usmania University. We are pursuing MTech here.
Sure.
So actually, by sharing your story, it's our story basically. We got placed in TCS and all in undergraduation, but our main interest is to pursue in core companies. So can you share your experience, like how you get back into the core companies or give suggestions to us for getting into the core companies?
Yeah, I think you're asking my personal thing questions. I thought you're asking, okay, giving me a job in the USA industry.
Not
So,
like
yes.
that, sir.
So, but that's okay. That's a fun part. Yeah. So actually, see, I think when you in the engineer level, right? So we focus on, like I was telling you, right? Just the design, simulation part, those small things, right? So if you understand the entire ecosystem, it is more important now. Every engineer should understand the entire ecosystem, right? So only when you understand the ecosystem, then you know what are the opportunities associated in the entire VLSI industry. Okay. So when I went out, so for me, you can say some kind of luck struck where I tried outside. Some VLSI companies were conducting some exams, and then I could crack them, and then I could go get a job, right? So, but now it is not that easy as well, because so many engineers are coming and things are on, right? So what you can do is like understand the entire ecosystem, what it is, then you will get to know what are the different opportunities associated with them, right? So, and then when you go to any VLSI, say if you want to pursue in VLSI career or something around that, right? So all they want to know is how much outside the designing you know, correct? So those are the things which as an engineer in VLSI, you keep trying to learn, understand surrounding things, and then you'll automatically get to know the opportunities available. Okay, that's the answer I can give.
Thank you, sir.
Thank you very much, sir. Thank you for sharing your insights about what are the hurdles and even the solutions also. What are the horizons new horizons that we can get from the hurdles itself. Thank you very much.